Welcome to The Explainer. Today, we are diving into one of the absolute cornerstones of organic chemistry, the nucleophilic addition reaction. We're going to use this fantastic visual guide to break down how one single, really predictable mechanism lets chemists build all sorts of complex molecules and even figure out what's in an unknown sample. So let's start with a big question. What is it about the carbonyl group, that carbon-oxygen double bond you see everywhere, that makes it such an irresistible target for a chemical attack? All right, let's get into it. The whole story really begins with a fundamental imbalance. It's all about an unequal sharing of electrons that basically hangs up a giant neon sign that says, "Hey, react with me!" And this visual just shows it perfectly. See, oxygen is way more electronegative than carbon. All that means is it's a bit of an electron hog. It pulls the shared electrons in that double bond towards itself. This little tug of war gives the oxygen a slight negative charge, and you guessed it, leaves the carbon a little bit positive and hungry for electrons. And in chemistry, that electron-loving carbon has a special name. It's an electrophile. It's the bullseye for this entire reaction. Okay, so how does this attack actually happen? Well, it's not just a random crash. It's more like a really predictable two-step dance that completely changes the molecule's shape and structure. And here's step one. The most important move. Our attacker is called a nucleophile. That's just a molecule with extra electrons it's happy to share. It sees that positive carbon and goes right for it. Now, before the attack, that carbon and its neighbors are all lying flat, what we call sp2 hybridized. But look what happens. As the nucleophile forms a new bond, it forces the whole structure to pop out into a 3D pyramid shape, which we call sp3 tetrahedral. This big change is the slow part of the reaction. It's the bottleneck. All right, on to the cleanup step. That pyramid-shaped thing we just made, the tetrahedral intermediate, it's super unstable. It's got a full negative charge sitting on that oxygen atom, and it does not want to stay that way. So in a flash, this part is super fast. It grabs a proton, which is just a hydrogen ion, from whatever's around in the solution. That neutralizes the charge, and boom, we have our final stable product. So now that we've got the mechanism down, we have to ask a really important question. Are all these carbonyl targets the same? Turns out, nope. Some are way easier to attack than others. And this is where the strategy really comes in. So here's the deal. Aldehydes almost always react faster than ketones, and there are two big reasons why. First, something called sterics. Think of it like this. Aldehydes have a tiny little hydrogen atom on one side, leaving a nice, clear landing strip for the nucleophile to attack. But ketones, they have two bigger, bulkier groups that basically act like bodyguards getting in the way. And second, there's an electronic reason. Those bulky groups on a ketone actually push a little electron density back towards the center carbon, making it less positive. And of course, a less positive target is a less tempting target. But get this. Here's a really cool exception that kind of proves the rule. You'd think benzaldehyde, since it's an aldehyde, would be super reactive, right? Well, it's actually less reactive than a simple one, like propanol. So what's going on? It's all about that benzene ring. It creates an effect called resonance. You can think of it like this. The positive charge on that carbon isn't stuck in one place. It gets smeared out and shared across the entire ring. Spreading out the charge like that acts like a shield, making that carbon way less positive and, a much less attractive target. Okay, enough theory. Theory's great, but let's look at some real-world examples. This is where you can really see just how useful and versatile this one simple mechanism is for actually making stuff. First up, adding hydrogen cyanide, or HCN. Now, on its own, HCN is actually a pretty weak nucleophile, so the reaction is painfully slow. But chemists have a trick. They add a little bit of base, which rips the hydrogen off, creating a negatively charged cyanide ion. And that ion is a much stronger attacker. When it hits a carbonyl, it forms something called a cyanohydrin, which is an incredibly useful building block for making even bigger, more complex molecules. Next up is a super clever lab trick. When you add sodium bisulfite to an aldehyde, something amazing happens. You form a solid, crystalline compound. Now, why is that so useful? Well, imagine you have a messy mixture of liquids and you just want the aldehyde out of it. You can just add the bisulfite, and the aldehyde will literally fall out of the solution as a solid. You can then just filter it off. It's a fantastic way to purify things.
And finally, what about using an alcohol as our attacker? Well, with a little acid to get things going, the reaction doesn't just happen once, it happens twice. The first attack creates a pretty unstable thing called a hemiacetal. But then, a second alcohol molecule comes in and attacks again, kicking out a water molecule and forming a much more stable final product called an acetal.
So why does any of this matter if you're not trying to build a new molecule? Well, this reaction has an incredibly powerful real-world application. It lets chemists see molecules that are totally invisible in a test tube. The key here is to use a derivative of ammonia as our nucleophile. Now, the first part of the reaction is exactly what we've already seen. The nucleophile attacks the carbon. But here's the twist. The intermediate that forms is unstable in a different way, and it immediately gets rid of a water molecule. So you get an addition, then a loss of water, and you end up forming a stable carbon-nitrogen double bond. And the possibilities here are just massive. Just look at this. By simply swapping out that little Z group on the ammonia derivative, you can create a whole family of different products. Things like imines, oximes, hydrozones. It's like having a molecular toolkit where you can just swap out the attachments to get a different result. And this is the ultimate payoff. One of those derivatives, 2,4-dinitrophenylhydrazine, don't worry, we just call it 2,4-DNP, is really special. When it reacts with an aldehyde or a ketone, the product it makes isn't some clear, boring liquid. No way. It's a bright yellow or orange or even red solid that crashes out of the solution. This gives chemists a dead simple, super fast visual confirmation. If you see that color, you know you've got a carbonyl. So let's just quickly wrap up the most important points. Remember, this whole reaction is driven by that polar carbon-oxygen bond, which creates that perfect electron-poor target. The mechanism is a reliable two-step dance: attack, then protonation. We learned that aldehydes are usually the more reactive targets because they're less crowded, and this single mechanism is a gateway to creating a huge range of important molecules, and it's absolutely essential for identifying them in the lab. You know, once you understand this fundamental mechanism, it's like learning the grammar of a new language. It just opens up this whole world of possibilities, which leaves us with one last thought. Now that you know how to spot the target, what other electron-rich challengers could you dream up to attack it and build something completely new?